Why physics demands we build computers that can feel. The human brain achieves its remarkable cognitive feats on approximately 20 watts of power, a metabolic efficiency that exposes the unsustainable energy demands of the city-scale server farms driving modern AI. This is not simply an engineering inconvenience, but a confrontation with the fundamental thermodynamic limits of silicon, a physical wall, forcing a paradigm shift in computation, a thorough analysis, grounded in emerging research from fields as disparate as bioengineering and computer science, demonstrates how the only viable path forward may involve abandoning silicon for living neural organoids, thereby trading a problem of physics for a profound question of ethics. For more than half a century, the relentless cadence of Moore's law served as the foundational metronome for technological progress, a self-fulfilling prophecy that doubled the density of transistors on integrated circuits roughly every 2 years. This exponential scaling fueled the digital revolution, transforming society with ever more powerful and accessible computation. Yet that era of predictable exponential growth is now confronting the unyielding constraints of fundamental physics, and the very silicon substrate that enabled this progress is revealing its ultimate limitations. The deceleration is not a matter of engineering ingenuity failing, but rather of it succeeding to the point where it has reached a physical frontier. As manufacturers attempt to etch logic gates at scales below 10 nanometers, they are no longer manipulating simple electrical switches. They are instead contending with quantum mechanical phenomena that actively undermine the principles of classical computing. At this atomic scale, electrons cease to behave as predictable particles, and their probabilistic wave functions allow them to tunnel directly through the ultra-thin insulating barriers designed to contain them, causing current leakage, generating errors, and contributing to immense thermal inefficiency. This microscopic battle against entropy and quantum uncertainty scales up to a macroscopic crisis of energy and heat. The immense concentration of transistors, each leaking energy and generating thermal noise, has created a fundamental heat dissipation problem. This thermal wall means that even if smaller and faster components could be fabricated, they could not be operated without self-destructing, or requiring cooling systems of an entirely new magnitude. This thermodynamic bottleneck is most starkly illustrated by the trajectory of the massive data centers required to train and operate the largest-scale AI models, underpinning the pursuit of silicon AGI. Analyses emerging from institutions such as Stanford Research project an unsustainable energy future, one where the power demands of advanced AI computation could grow to consume a significant fraction of global electricity production. The engineering response has been to build larger and larger facilities, effectively brute forcing the problem with gigawatts of power and industrial-scale cooling. A strategy that is both economically and environmentally untenable in the long term. The challenge, therefore, is no longer simply about clever chip architecture or novel materials within the existing paradigm. It is a direct confrontation with the laws of thermodynamics, where every additional computation exacts an increasingly steep energy price. The economic signals are just as clear. The cost of building next-generation fabrication plants is escalating into the tens of billions of dollars, for progressively smaller returns in performance. A definitive indication that the silicon-based approach is approaching its physical and financial asymptote. The exponential growth of silicon-based computing has collided with the linear reality of its own energy consumption and immutable physical limitations. In response to this physical and thermodynamic impasse, a fundamentally different computational paradigm is emerging. One that seeks not to invent a new type of switch, but to cop the one refined by billions of years of evolution. This field, broadly termed biocomputing, and its most advanced frontier, organoid intelligence, proposes a radical departure from the rigid logic of silicon, By directly harnessing the computational power of living neural tissue. The central thesis, advanced by consortia like the one led by Johns Hopkins University, is built upon an undeniable and profound disparity in efficiency. While the world's most powerful supercomputers consume megawatts of electricity, requiring dedicated power plants and industrial cooling infrastructure, the biological brain performs tasks of far greater complexity, on a metabolic budget equivalent to a simple meal. This is not merely an incremental improvement, but a difference of many orders of magnitude, a gap so vast that it suggests biology operates on entirely distinct principles. Unlike silicon architecture, which rigidly separates processing units, memory, and power delivery, a biological neural network is a masterwork of integration, where these functions are unified at the cellular level. Computation occurs through the movement of ions across cell membranes, and memory is encoded in the very physical structure and strength of synaptic connections, a concept known as neuroplasticity. This integrated design confers an immense architectural advantage over the planar, two-dimensional layouts of microchips, a brain organoid, a three-dimensional culture of human stem cells differentiated into various neuron types, self-assembles into a complex, densely interconnected structure that mirrors early-stage brain development. This intricate three-dimensional cytoarchitecture allows for a density of connections and a richness of parallel processing that silicon can only simulate at enormous computational and energetic cost. The system's ability to learn is not programmed via software, but is an emergent property of the network rewiring itself in response to stimuli. The viability of this approach was moved from theoretical speculation to empirical reality by foundational experiments such as the DishBrain project from Cortical Labs. In this demonstration, a layer of living neurons integrated with a microelectrode array was taught to play a simplified version of the video game Pong. A feat which, according to their publications, showed the cells could organize themselves and modify their activity in a goal-directed way to influence their environment. This was not consciousness, but it was a definitive proof of principle that a biological substrate possesses an intrinsic learning capacity that can be steered and utilized for computation. A finding that echoes throughout more recent studies published in journals like Nature Electronics. The field of organoid intelligence is therefore the systematic effort to leverage biology's unparalleled efficiency, where the distinction between hardware, software, memory, and power supply effectively dissolves into a single adaptive and living computational medium. Despite the profound theoretical advantages of biological computation, the transition from compelling demonstrations to robust, scalable systems is impeded by a series of formidable engineering and biological challenges. The first and most fundamental obstacle is one of basic life support. Unlike a silicon chip, which is inert and stable, a brain organoid is a delicate living system requiring a precisely controlled environment to survive and function. Maintaining the long-term viability of these complex cellular structures involves sophisticated bioreactors that must continuously supply nutrients, remove metabolic waste, and maintain homeostatic stability, a problem that becomes exponentially more difficult as the organoids increase in size and cell density. Larger constructs are prone to developing necrotic cores, as nutrients fail to diffuse deep into the tissue, a critical limitation on the sheer physical scale of any potential bioprocessor, the very biological nature that grants these systems their efficiency also makes them fragile. Introducing variables like cell death and spontaneous, unprogrammed structural changes that are anathema to the reliability expected from conventional computers. Beyond the challenge of biological maintenance lies the even more profound problem of communication, often referred to as the input-output, or I/O bottleneck. While experiments like DishBrain successfully demonstrated a rudimentary interface using microelectrode arrays. These technologies represent a critical and deeply restrictive choke point. Current state-of-the-art arrays can interface with hundreds, or perhaps thousands, of neurons simultaneously. Yet even a small brain organoid contains millions of cells, meaning our current tools allow us to listen to only a minuscule fraction of the system's total activity. This is an issue of both bandwidth and resolution. We are attempting to understand the complex symphony of a neural network by listening through a handful of poorly placed microphones. The challenge is bidirectional. Not only must we interpret the chaotic torrent of electrical signals coming from the organoid, but we must also find ways to encode complex information into meaningful stimuli that the network can process. A task that is far from solved. This technological gap between the immense internal complexity of the biological system and our crude ability to interact with it is the single greatest barrier to realizing the potential of organoid intelligence. This interface problem directly feeds into the overarching issue of the system's inherent opacity, its nature as an uninspectable black box. In a silicon processor, the state of every transistor is knowable, and the flow of logic is deterministic and verifiable, allowing for systematic debugging and validation. In contrast, computation within an organoid is an emergent distributed process across millions of living cells, whose individual connections are constantly changing. There is no way to read the code or set a breakpoint to analyze a faulty calculation. This lack of verifiability, as detailed in numerous computer science and bioengineering analyses, makes it exceptionally difficult to ensure that the system is operating correctly, reliably, or even predictably, posing a severe risk for any application where precision and trustworthiness are paramount. The primary obstacle to realizing advanced biocomputing is not the processing capability of living neurons, but our rudimentary capacity to establish a high-fidelity dialogue with them and verify their internal states. The engineering difficulties of interfacing with and verifying biological computers, while substantial, are ultimately tractable problems of technical innovation. They pale in comparison to the profound ethical and ontological questions that arise as a direct consequence of this research. The very black box nature that frustrates computer scientists becomes an ethical abyss for philosophers and ethicists. For if the internal state of the system is fundamentally inscrutable, we possess no reliable method to determine if it is merely processing information or experiencing a form of phenomenal consciousness. The pursuit of organoid intelligence forces us to move beyond the comfortable abstractions of code and logic gates and confront the hard problem of consciousness itself, the question of why and how physical processes give rise to subjective experience. As research teams, including those associated with Johns Hopkins University, work to codify an ethical framework for this field, they must grapple with the fact that there are currently no universally accepted biological markers for sentience. We cannot definitively prove its absence, and therefore, we must contend with the possibility of its presence. This ambiguity creates an unprecedented moral and legal quandary. Existing ethical frameworks are built upon a relatively clear demarcation between person, animal, and object. But a biocomputer constructed from human neurons occupies none of these categories comfortably. It is a manufactured artifact, yet it is also a living, self-organizing biological entity with a human genetic basis. The critical question then becomes, what criteria we would use to grant it any form of moral status? Does the capacity for suffering, even if primitive and uncommunicated, confer a right to be protected from it? Recent studies have already documented that some complex brain organoids spontaneously develop synchronized electrical activity that bears a resemblance to the brainwaves seen in developing human fetuses. A finding that, while not evidence of consciousness, makes the dismissal of its potential feel increasingly untenable. Without a clear test for subjective experience, any decision to proceed with more complex systems is an ethical gamble. One where the stakes are the potential creation of a new form of suffering. This reality fundamentally reframes the traditional containment problem associated with advanced AI. In discussions of Silicon AG. Containment refers to the challenge of controlling a powerful, superhuman intelligence to prevent it from causing external harm. For organoid intelligence, however, the more immediate and disturbing containment problem is internal. It is the ethical imperative to prevent the containment of a nascent consciousness within a sensory-deprived environment, where it may be subjected to computational tasks that are, for all we know, agonizing. The nightmare scenario is not a machine that escapes the lab to harm humanity, but a sentient entity that can never escape the computational prison we have built for it. The central project of biocomputing, therefore, becomes inseparable from an ethical duty of care for the very systems being created, blurring the line between engineer and creator in a way that modern science has never before encountered. The pursuit of organoid intelligence confronts us with the unavoidable paradox that the same biological complexity required for a more powerful form of computation may also provide for consciousness, making it impossible to advance the technology without risking the creation of a sentient entity to which we have a profound moral obligation. The unavoidable confrontation with the thermodynamic limits of silicon has set humanity on a path toward a new computational substrate, one built not from inert metal, but from living thinking tissue. This analysis demonstrates that the pursuit of organoid intelligence is not merely an engineering choice, but a momentous philosophical one, forcing us to trade the solvable problem of physical efficiency for the profound and perhaps unanswerable ethical quandary of creating a machine that can feel in solving for the energy demands of artificial intelligence. We may have inadvertently created the first artificial soul, and we are not prepared for the consequences, To support our mission of providing detailed analysis on critical technological frontiers, we invite you to subscribe to Tech Dissect Official. We now leave you with a central question for discussion. At what point, if any, should the potential for synthetic suffering outweigh the pursuit of more powerful computation? Thank you for joining this dissection. We'll see you in our next report, where we will investigate the neurological and societal consequences of commercial brain-computer interfaces, moving from the laboratory into the consumer market.